You're allowed 4 in the multiple choice and 2 in the problem set. 23. What else?
Maybe 21.
21?
Is that what you said?
21?
17.
15.
15?
The problem with 15 is...
Well, whether it was negative.
Right. The problem wasn't clear which way to define positive.
Yeah, whether east or west was positive or negative. So yeah, that could be.
So let's I'll give you a hint on that. You would define east as positive.
Well, correct.
That's the opposite of what I
Yeah, that's the opposite of what I had to.
Oh,
So
yeah.
does that mean that we can erase that one and pick that up?
Yes.
It just changes the sign.
Yes.
East is positive.
East is positive. We haven't set these in stone yet, so I'm just writing them down for now. So you haven't selected these officially yet. So 15 is on.
Well, that's exactly what I just changed. You had to say that. Yeah. Well, no, that's if it is. No, originally that's what I had. See, I had to make that.
So you don't need any more.
Oh, yes, I'm sure we do. I think it's a little.
Yeah. Yeah, these is positive.
In the problem section, number 3 and 7.
Number 3 and 7.
Number 3?
And 7.
Yeah, number 3 was interesting.
Yeah.
That's not too bad.
5 minutes. What'd you get?
You write 17 on the other ones. Well, anyone wants to argue with you, that's fine.
And 10.
Oh, I didn't know. Did you want to?
There's 9.
Yeah.
And this is what we have so far.
Yeah, I started looking up this oh my god particle that it was traveling. It's a particle in the atmosphere, like 51 joules or something. That's about all I know.
Does it cause any black holes?
No, I was actually also looking up artificial black holes. And you know how in like a sun, like a super, like if you're doing rockets, you have a supersonic cone, how you compress it and it breaks through the barrier at that little point. Well, they're trying to use quantum fluids. Remember that Bose-Einstein condensation? The quantum fluid is like Bose-Einstein condensate. So as they want to accelerate it to the speed of light, and as it gets into this,
Sort of plume.
right, and it creates like a sort of event horizon, and that way you can sort of try and quantify like Hawking radiation. Well, if you're near the event horizon, you don't know where you are. You don't know if you're ahead of the event horizon or behind it. But they're trying to determine if you're ahead of it or behind it by measuring Hawking radiation, and because it would send a particle and then an antiparticle, whichever one you get, that's what you decide for.
That particle formation would have to occur right on the boundary of the event horizon.
Right.
So that you actually form one on one side and then form a particle on the other side.
Right.
So you'd actually have radiation coming from the black hole.
Right.
Wow. Cool.
I was going to save that for quantum day, but
Yeah.
we just let the cat out the bag.
I think we'll have time to look at these problems. So what I'd like to do is do a relatively short presentation on general relativity. Let's take a look at that. give you a handout of this because, as you probably have noticed over the course of this semester, I've been changing a lot of these lectures, you know, as I go along. Put a lot of work into it, and this one I've changed so much that I just figured, okay, I'll just print out a copy and hand it out. What's that? Yeah. It's already printed, but this is. Well, we probably take it for granted about mass, but if you really spend some time thinking about it, there really are two kinds of mass in our everyday world. There's mass associated with gravity. Mass has a property that causes a gravitational attraction, at least in the Newtonian world, a gravitational attraction between other masses given by the force of gravity, Newton's force of gravity, which is one way to look at mass. But there's also mass that measures inertia in Newton's second law of motion, which basically says that there's a net force on something. That force is proportional to the mass of that object, and so mass is a proportionality that helps to measure the resistance to the change of motion of an object, inertia. Well, Einstein thought that this was pretty interesting. The mass would actually have these two distinct properties, one of gravity and one of inertia. And it was Einstein's view that the dual behavior of mass was evidence that there actually was an intimate and basic connection between these two behaviors of mass. Here's Einstein's reasoning. Mass gravitational and mass inertial are directly proportional by a gravitational constant G. There's a basic connection between them. No mechanical experiment could distinguish between these two values of masses. And in fact, Einstein extended this idea to say that no experiment of any type could distinguish between two masses. Equivalence. Equivalence was Einstein's happiest thought. That's how it goes. In 1907, Einstein had what he calls the happiest thought in my life. In 1907. What was this thought?
Was it a dream?
It could have been a dream. It could have been a memory. It could have been the memory of his first marriage to Maleva. Yeah, what's that? It could have been
Buy one, get one free at the hot dog stand.
the thought of his future marriage to Elsa. Yeah, that wasn't that. It could have been the thought that he has published 4 gigantic papers in 1905, of which he is about to receive the Nobel Prize. No? Because he had an agreement in his first marriage when he got divorced that any money he got from the Nobel Prize would go to his first wife. So,
Are you serious?
I'm serious.
Oh,
He had
wow.
an agreement.
No.
Yeah, because she helped him. She was better mathematically than he was. And so she helped a lot of the mathematics that helped him do the
So
stuff that
all
he did.
of the money went to her? That's
As it turned out, I don't think he gave her the money.
Okay.
But that was the agreement. It just didn't quite work out that way. So that was not his happiest thought. You disagree that? No, Einstein's happiest thought was that if he were falling from the roof of a house, he would, it would appear like there was no gravitational field on it. If you were falling, in this case, along with a scale and a ball, it would appear that in his frame of reference there was no gravity. That was his happiest thought of his life. And to extend this thought, conversely, an observer in a closed box, such as an elevator or a spaceship, cannot necessarily tell if his or her weight is due to gravity or acceleration. That is a happy thought. How could he tell the difference between gravity and acceleration? You can't. Here's an example. We have a fellow in an elevator. This observer is at rest in a uniform gravitational field directed downward. He's standing on an elevator on the surface of a planet. Our planet. He feels pressed into the floor due to the gravitational force. If he releases his briefcase, it will move toward the floor with an acceleration of gravity. So he releases the briefcase, it falls towards the floor with an acceleration equal to gravity. There should be, as usual, the vector symbol did not. Can't be found on different version of PowerPoint. All right, well, you just have to imagine a different arrow above that. So we'll go on from there. All right.
J hat.
Yeah, looks correct over here. Now here's another example. Let's say this elevator is accelerating upward with a magnitude equal to the same acceleration g. So the observer is accelerating upward in this elevator. The force is producing an upward acceleration, A equal to g. The person feels pressed to the floor with the same force as in the gravitational field. If he were to release his briefcase under these conditions, it would again accelerate towards the floor with acceleration equal to g, just like if you were on the surface of the planet in a gravitational field. No difference. Being the observer within this elevator, he wouldn't know which was gravity, and which was the fact that his frame of reference was accelerating. So here's a conclusion. Einstein claimed that these two situations were equivalent. No local experiment could distinguish between those two frames of reference. One frame is in an inertial frame in a gravitational field. The other one is accelerating in a gravity-free space. And that's the principle of equivalence. That accelerating in a gravity-free space is the same as being in a gravitational field. So they're equivalent. Well, let's take our same observer in the elevator, and let's suppose there's someone at rest outside the elevator who has a flashlight. Turns the flashlight on, and to the both observers, so they're both at rest, they both observe a light beam that is horizontal across this elevator. So to the observer at rest outside, they see a straight horizontal line. To the observer in the elevator, they see a straight horizontal line, light beam. Let's say we have an elevator that is moving at constant velocity with respect to a outside observer who's at rest. To the outside observer, they're going to turn the light on. Again, to them, they will see a horizontal light beam. To the observer inside the moving frame of reference, it will be a straight light beam, but it will be angled, not horizontal, due to the relative velocity of the two frames of reference. let's say you had an observer in a moving frame of reference moving with an acceleration, constant acceleration. Now, if you have a light beam in that person's frame of reference will be curved. It will appear curved. It will still appear straight to the person at rest, but the person who's in the accelerated frame of reference, they will have a curved light beam. But if that beam of light curves in an accelerating elevator, then the equivalence principle that we just established says that the beam of light should also curve in a gravitational field. There's no difference between an accelerating frame of reference and a gravitational field, yes.
Well, that reminds me, there's a solar eclipse coming up.
I'm going to mention the one in 1918 that helped prove this.
There's one in like August 1st or something.
August 1st? Where?
I think it's NASA's webcasting it live all over the world, but I think it's in like Russia or something.
A full solar eclipse?
Total, yeah.
Total solar eclipse?
Yeah. Have you heard about it also?
Yeah, but I don't remember where it
It like starts out in an area and travels. I was watching a video on late at night. But anyways.
We're going to have one here in 2017,
Wow. I might
up in Tennessee.
Oh.
So if you travel up to, say, northern Tennessee, it'll be a full solar eclipse
It's gonna be a big church.
here in the United States. That'll be the first one in the United States.
Really?
Yeah, in a while.
Yeah, don't guess any of y'all saw the 1983 eclipse that went through Montgomery and
1983,
Yeah.
Montgomery, went through Montgomery.
and Atlanta.
Of course, we have to survive the end of the world in 1912 first.
Yeah.
To get to this. So
I thought that was
that is a great idea. I need to go to Russia. I need a field trip.
well, the webcasting it. So
I
you
think
know,
it's pretty
That's the same.
I guess
It
it's not
can't be the same of being there and then seeing the whole daytime sky.
I might not come back because I just like it. It's cold.
It's not just that the light goes dim, it's the temperature drops about 20 degrees. But they're going from daytime to nighttime conditions.
See, we need one in Texas that way every day.
That way, Texas would be worth going to.
Yeah, I might actually like it.
Well, here's a conclusion. Einstein proposed that a beam of light should be bent downward by a gravitational field. The bending would be small. The laser would fall less than 1 centimeter from the horizontal after traveling 6,000 kilometers. And experiments have verified this effect. So that would be some support for this theory. So we have the postulates of general relativity, principle of equivalence. All laws of nature must have the same form for observers in any frame of reference, whether accelerated or not. In the vicinity of a given point, a gravitational field is equivalent to an accelerated frame of reference without a gravitational field. Implications. Gravitational mass and inertial mass are not just proportional, but completely equivalent. A clock in the presence of gravity runs more slowly than one where gravity is negligible. The frequencies of radiation emitted by atoms in a strong gravitational field are shifted to lower frequencies because the gravitational field is going to take some of their energy away. This has been detected in the spectral lines emitted by atoms in high-mass stars. So that's support for this theory. Other implications. The gravitational field may be transformed away at any point if we choose an appropriate accelerated frame of reference. A freely falling frame. All this was continued in thoughts of Einstein by a certain quantity called space-time. Einstein defined the curvature of space-time to account for the gravitational effects at every point in space. In fact, you could possibly think of space-time and gravity as being one and the same. That the fabric of the universe, space-time, is defined by the fact that there's gravity, and vice versa. Curvature of space-time. According to Einstein, there's no such thing as a gravitational force. Instead, the presence of a mass causes a curvature of space-time. 4-dimensional space, 3 dimensions of space, and 1-dimensional time, space-time. In the vicinity of the mass. So the presence of a mass curves space. And that's what Einstein is saying is gravity.
Would our curved space look like anything like a vector field the same way as, say, a magnetic field or an electric field?
What do you mean, like the field lines?
Just, I mean, if you've got an object, say the mass is acting like a pole on a magnet, would the lines just be analogous to, say, magnetic lines that go from one pole to the other?
I mean, you could think of it that way in one sense. Certainly, that is the goal of theorists who are basically involved in trying to bring a universality to all the laws of physics, all the forces of physics.
Okay.
And hence they're trying to think of gravity in the same way as they think of these other forces.
Okay.
This in itself is kind of independent because in those forces you have
Positive and negative.
particles.
Mm-hmm.
Oh.
Yeah, you have particles and positive, negative. You've got
Electrons.
right gravitons. There would be gravitons, which in this theory is saying that the space is smooth and continuous. And there's a property of space, of gravity in space, that deforms in a continuous manner. So they're, in a sense, they're kind of contradictory.
I saw this real cool video online. They took a giant sheet of rubber or whatever, they painted lines all over it, and they put a camera directly above it. And if you look at it, it looks like a plain checkerboard. And when you mass in there, it looks like a plain checkerboard. But when you change, like if you look at it from a different angle,
Orientation.
you can see the curvature, but when you go back above it, it looks like a plain checkerboard.
So it's a matter of perspective in a sense too. This stuff is fascinating. Going back in time. This curvature dictates the path that all freely moving objects must follow. So, in essence, mass will deform, or not deform, will shape the space-time in its vicinity, and then other masses will be affected by that. Think of it this way. The effect of curvature of space-time. Imagine two travelers moving on parallel paths on the surface of the Earth. Let's say they start a few meters apart. Well, they start a lot of meters apart. On the surface of the Earth, heading exactly northward. As they approach the North Pole, their paths will be converging. They're just traveling on straight paths, and they're both traveling towards the same destination. But the general effect is that they start moving closer to one another. So the fact is that they're actually moving on a curved space. Right?
Oh, that's
Not on a
because
flat space, but on a curved space.
that's because in spherical geometry, all parallel lines intersect.
Spherical geometry.
Non-Euclidean space.
Non-Euclidean space on a geodesic.
Yeah, I think there was this one mathematician called Point Carey or whatever.
Okay.
And he was trying to, like if you draw it in parallel lines, they all intersect at one point.
In that space.
Right.
Right.
I think it was called like Point Carey space. I can't pronounce it.
Well, in the context of this, these two people, will actually move towards each other as if there were an attractive force between them, but it's only because they are defined by their space and how they travel on that. So it's the geometry of the curved surface that causes them to converge rather than an attractive force between them. So, here we have a mass with gravity, and space-time has been changed in the vicinity of this mass. And so it would be one prediction that even light itself would be affected by this change in space-time in the vicinity of that mass. And light itself will be deflected from a straight line path, as we normally see it, into the shortest path in space-time. And even other objects, like if this were the sun, and other objects like the Earth would be confined, not because the sun is pulling on it, but because the Earth itself is following the shortest path in four-dimensional space-time. Another way to look at this, we're accustomed to looking at flat maps on the surface of the Earth to find the shortest route between two places. For instance, if I wanted to go from New York to Kamchatka, I might think that that might be the shortest way on a flat two-dimensional map. But in reality, we're on a curved surface. I'm not sure I spelled Kamchatka right. I probably did. But I know it goes Kamchatka.
There's a T in there.
There's a T in there?
T.
T?
C-H-N-T.
Kamchatka was always key in the game called Risk.
Yeah, I only remember because I played
It's
that.
like you're traveling the long way. I traveled like,
You travel over the North Pole.
yeah. And if you actually look at it, if you look at the lines, they're actually curved.
Wait, on the Earth, you'd want to choose any kind of great circle that has its center in the center of the Earth,
Just take like a rubber band, wrap it around.
as long as it was a circumference of the Earth. And so it wouldn't necessarily have to go over the North Pole, but it would have to go across that radius of the Earth where your center was the center of the Earth. That would be the shortest distance between two points.
You've got a
Yes.
globe.
What's
If
that?
you have a globe and you want to find the path that's the shortest distance, just take a string and put it on the 2 points and pull it tight, and that'll give you your direction to travel.
Basically, that's what you would do on a space-time, four-dimensional, four-dimensional graph. Thought this was fun. Does that crack in Einstein's theory of relativity? Nothing's perfect. So here's a summary. Mass number 1 tells space-time how to curve. Curved space-time tells mass number 2 how to move. The average curvature of space-time is proportional to the energy density. Mass is the same as energy, so even energy density could curve space-time. The actual equation could be solved for the metric, which can be used to measure lengths and compute trajectories. We're actually not going to go into the mathematics of general relativity. That would be a basis for a very long course, a very complicated course. So we're just highlighting the nice features of it. Testing general relativity. General relativity predicts that a light ray passing near the sun should be deflected by the curved space-time created by the sun's mass. Einstein came out with this theory of general relativity in 1916, actually during the First World War. And coincidentally, in 1918, there was going to be a full solar eclipse. And so some bright people decided to test Einstein's theory of general relativity at that time. And the idea was to see if a distant star would be reflected during the eclipse, if you could actually see a star that was actually behind the sun during the eclipse. As it turned out, it was possible to see a distant star that should have been behind the sun because it was deflected by the gravity of the sun.
Is that seconds?
Yeah, it's a very accurate measurement, 1.75 seconds. So even with the sun's incredible mass, this is a very, very small effect.
So does that not mean that if we could travel the speed of light, decided to go to another solar system, we could head towards the solar system at the speed of light and just totally miss it?
Yeah.
I mean, you see it, but you go.
Yeah.
Yeah, you didn't calculate that bump in the road there.
Yeah.
Due to that star or something.
I wouldn't get too close to a star. Find out, figure it out.
Yeah.
Or a black hole, definitely a black hole.
Oh yeah.
Here's another effect, Einstein's cross. 4 spots are images of the same galaxy. They have been bent around a massive object located between the galaxy and the Earth. The massive object acts like a lens. So this is one way that you can use what is called gravitational lensing to look at very distant objects that you normally wouldn't be able to see because that light is bent towards us like a lens would bend the light towards us to focus it. So you have to see 4 images of the same object here.
It's not a smooth lens then.
Yeah. Here's Einstein's gopher. Evidently there was a massive object and there's a gopher behind the massive object. And we see a gopher 4 times. Of course, not perfect images because they're all looking in the direction.
That's not in your handout.
I had to put something in there. Other verifications of general relativity, explanation of Mercury's orbit, which had a discrepancy between observation and Newton's just theory of gravity. Time delay of radar bounced off Venus. Gradual lengthening of the period of binary pulsars due to the emission of gravitational radiation, and so forth and so on. A list of probably hundreds of things that would support the theory.
Gravitational radiation.
Huh,
Graviton?
maybe. I mean, it is presumed, if you look at the quantum mechanical aspect of things, that there should be a particle called a graviton. Because all other forces have.
That was predicted
Elementary
with
particle.
string theory, wasn't it?
I think before string theory, but now string theory is trying to bring everything together. String theory is trying to merge this continuous idea of general relativity with the discrete idea of quantum mechanics. That's what string theory is trying to do. Black holes. One other thing that general relativity would predict is that there should be things called black holes out there. The concentration of mass is great enough that black holes believed to be formed. In a black hole, the curvature of space-time is so great that within a certain distance from its center, all light and matter become trapped. That radius is called the Schwarzschild radius, also associated with what is called the event horizon of the black hole. That would be about 3 kilometers for a star the size of our sun if it were to collapse into a black hole, but actually our sun would not do that. It's too nice. It's not massive enough. At the center of the black hole is a singularity. It's a point of infinite density and curvature where space-time seems to come to an end. So this is a complication for trying to figure out the mathematics of general relativity to have a singularity in your mathematics. Major events involving massive objects might cause ripples in the space-time fabric. I added this just for you. These gravity waves are being searched for. 5. The Laser Interferometry Gravitational Wave Observatory, otherwise known as LIGO. Laser Interferometry Gravitational Wave Observatory. Here is LIGO. How does LIGO work?
Well, we already talked about the medicine order.
So it basically uses the idea of the Michelson-Morley interferometry. If you run one laser in one direction, or you split it and you have it interfere with itself, if there were a gravitational wave, then that effect might change the speed of light in one direction, hence you would observe an interference pattern. And there's 2 facilities, one in Livingston, Louisiana, the other one in Hanford, Washington. And the idea is that you have redundancy, for one thing.
Seismic events.
And seismic events, and also, I would think, a differential effect as well, so that if you have 2, kind of like the way they use differential GPS, if you have 2 sources, that allows you to eliminate some of the noise.
Which is very easy to track the noise.
Yeah.
Stomping around.
Right, just walking around.
Wouldn't put that anywhere near here.
Yeah. Anywhere near this campus.
Yeah.
Yeah, just walking around might cause a gravity pain.
What
Or
is
at least,
it?
what appears to be one. So I'm not on the bandwagon that this can be done yet, personally, because I just think it's too hard.
Are those 2 lines running off from each building part of the structure?
It's like 4 kilometers in one direction and a couple kilometers, like 4 and 2 or 4 and 4. I think there's different plans. But yeah, it's like 4 kilometers and they're perpendicular to each other. And there's like a half silicon barrier, whatever,
Yeah.
splits it off in one direction and another direction, and then they come
Just
back.
take over.
They should be at like the same point.
Oh, you got it.
I'm so excited.
Actually, I do have a picture of the inside of this where you can see what it looks like. So, yeah. What? Am I that bad? Am I that predictable?
I like it, go ahead.
Here's what it looks like on the inside of the LIGO. They evidently have workers working all over the space-time.
I like that.
I've never seen that before.
I'm sorry, this is not LIGO.
Lego.
Lego. No, this is how it looks on the inside. So really not too many people around. There's a lot of bright metal objects.
Yeah, I was looking at one in Germany, and what they built was like these 2 really dense masses, and they were trying to measure an oscillation between the 2 really dense masses.
Any results yet? 'Cause I know
Oh
they-
yeah. Actually, like recently, they've actually, because see, they have to get it down the wavelength of these gravity waves. Theoretically, they'd be like the size of gametes. So the frequency of these things are going to be really small, and they've gotten down because they have to measure a frequency of like 10 to the minus 24, which is just amazingly small.
And that's
almost
why I just
Planck's.
don't think.
We're almost getting down to Planck's constant.
Right.
So it's pretty.
So you're almost limited by uncertainty principle.
Right, yeah, there's a lot of those quantum, so uncertainties everywhere.
Wow. That's it for this lecture.
Structural, you and Jason talking about photon particles. What exactly are those? I've got a rough idea, but I don't think it's right.
Jason?
Yeah, exactly.
You know, I don't think a lot of people actually know. I mean, it's just like theoretical particles that should be there.
Does it have to do with, like, magnetic waves? Isn't,
I think that's you, the boson, the Higgs boson would be like what gives things their mass.
why?
No, I think a boson is, it's, I don't know, for some reason I want to think you can split a boson particle. I think we've tried to split a boson particle and call it a bunch of different particles or something.
Well, the reason I asked that was I read something about particle to deal with.
But you gotta remember, these things aren't actually particles. It's like packets of energy. I don't know. Yeah, it's crazy. You can't really detect it. You just theorize about it.
All right, back to special relativity. How do we feel about these numbers here? Do we wish to make any changes? Actually, I think you made good selection. I think those would be the ones I probably would select. But any opinion against this?
That number 10 would be like almost impossible to do if you didn't have a TA, because I couldn't do it on my TA anymore.
Oh, really?
Is that the one where we had to carry it out to about 11 different
It
significant?
was 1 and 13 decimal places out.
Wow. So you did it exactly.
You had to, you didn't like it.
I did use approximation.
On number 3, now that's when I had to carry out decimal places like crazy. And that word problem. Yeah, I had to.
I was like, I'll get it.
Yep.
I had to. I mean, on part A, I did an approximation. On part B is when I had to carry it out.
Okay, should we try these out? Let's start with number 10. So the jet plane travels around the world at 2,000 miles per hour, 894 meters per second. 2 accurate atomic clocks measure the times of flight, one on board the plane and the second on Earth. If it takes 12 hours to complete the journey, what will the time difference in microseconds be? Now, when I read this problem, I noticed there was one small problem with this problem.
Velocity of the Earth.
2 small problems. I didn't even assume anything about the Earth moving. That's a great problem.
Which way is it traveling? Due east or west? Or?
Well, it says it takes 12 hours to complete the journey, but it didn't say whose time frame the 12 hours was in.
That's good.
So it didn't say whether it was the person in the jet plane or whether it was the person on the ground. As it turns out, if you do it either way, you get the same time difference between the two. So it doesn't matter. But you've got to assume one has the 12-hour clock and the other one does not. So what I assume is the person on Earth had the clock. Right? So on Earth, delta T is 12 hours. And the moving clock runs slow. This would be consistent with an approach like in the twin paradox, because the person who's traveling around the Earth is actually accelerating in a centripetal way around the Earth. So you can really be sure only of the rest person. And so the moving clock is the one that's running slow. So our difference in time between the Earth observer and the moving observer has the proper time, because they're with write as 1 minus, now 1 over gamma is 1 minus velocity over c squared to the negative 1/2 power delta t, correct? That's 1 over gamma. Oh, 1 over gamma would be just to the 1/2 power. Okay. So, what we got is, what I did was a binomial approximation. So this velocity is really, really small compared to c. This is the velocity of the plane, which is only 894 meters per second. If it's really, really small, then we can take this out to a binomial expansion of just the first term. So what I did was I got 1 minus, this is 1 minus 1/2 b over c squared. So all I did was take it for the first term, drop that 1/2 down because x is really small compared to 1. So 1 minus 1, then we have a minus minus, so that's going to be 1/2, positive 1/2, velocity over c squared delta t. So that's going to be 1/2, 894 over speed of light, all that squared, times 12 hours, and there's 3,600 seconds per hour. So that would give us the total time difference in seconds. That gives us 1.92 times 10 to the minus 7 seconds. So that is 0.19 microseconds.
That's what we got.
Yeah, that's right.
We got 1.19 times 10 is negative 7.
What do you think?
Would ask you to explain the binomial expansion as applied to physics, but probably don't have time.
Yeah, basically just, if you got 1 plus x to the n, and x is really small compared to 1, then this is approximately 1 plus n times x on the first term. All the terms are going to be, plus something x squared, plus something x cubed, blah, blah, blah. But if x is really small to begin with, then x squared, x cubed, x fourth are incredibly small.
Sort of like how we did coefficients of expansion.
Right. So you can make that little approximation. All right,
That's
nice.
what I had to do back in the day.
Exactly. When you had to use slide rules like my dad said.
And I just want to learn for nostalgia's. Well, it's like a piece of history.
Here's 17. An electron has a kinetic energy that's twice its rest energy. Determine its speed. Well, last time, we came up with this equation. The kinetic energy in a relativistic sense is equal to gamma minus 1 times the rest energy. And so, in this case, if the kinetic energy is equal to twice the rest energy of the particle, then it must be true that gamma minus 1 is equal to 2. Or gamma equals 3. If gamma is equal to 3, we had another little formula that we introduced the other day, just so you could convert velocity if you knew what gamma was. And that formula looked like this. minus 3 squared. And that comes down to yeah, the gamma is 3.
I like that one better. You had the square root of 8 over
I did the same.
square root of 9 times c.
I completely forgot about that one.
Yeah. Well, see, I just, yeah.
It's a nice one for some of these problems, it's a nice one to use. Sound good? 21. Yeah, 21. Assume a gram of a substance marked as pure energy is annihilated by a gram of a second substance, anti-pure energy. Yes.
I was just wondering, I wasn't too sure about this pure energy and non-pure energy, but I assume the mass would have been double.
That's right.
What you would think.
It was double the energy of problem number 20.
Yes. You still want to do it?
I didn't want to start with.
Oh, okay. You get outvoted. How long would the energy release power a city that uses 10 to the 9 watts of power?
P equals E.
So let's first calculate how much energy we're talking about. So we're talking about MC squared. We're talking about 2 grams of total substance. The pure energy and the anti-pure energy. So that's going to be 2 times 10 to the minus 3 kilograms times the speed of light squared. And that comes out to 1.8 times 10 to the 14 joules. Not the energy of a thunderstorm. And since energy will equal power times time, time will equal energy divided by power. So in this case, we got 1.8 times 10 to the 14 joules divided by 10 to the 9 watts, which is a joule per second. So in terms of seconds first, 1.8 times 10 to the 5 seconds, which we don't have that possible answer, we have in terms of hours. So we're going to say that there's 1 hour for 3,600 seconds. And so that comes out to 50 hours. Sound good?
I wonder if you can accelerate these particles. That'd be crazy.
Or because it'd be like general relativity. So far, so good. 23. I can see as I look out there, a lot of you already have these that way, so you're kind of thinking, should have selected something else. But is a spacer from another galaxy passes over the solar system directly above a radial line from the sun to the Earth. We measure the distance to be 1.5 times 10 to the 11 meters. On Earth, the spaceship is observed to be traveling at the speed of 0.8 c, for which gamma is equal to 5/3. So that's kind of nice to do that for you. As measured on Earth, it takes the spaceship 625 seconds to travel from the sun to the Earth. When a scientist in the spaceship measures the Earth-Sun distance and the time it takes her to travel that distance, she finds the results are respectively, well, 11 meters. That's for an observer on Earth, observing the length between the Earth and the Sun. But the person in the moving craft is going to see that length contract. So for the mover, she's going to see a contracted length equal to L naught divided by gamma. And that's going to be equal to 1.5 times 10 to the 11 divided by 5/3. In this case, which is going to be 9 times 10 to the 10 meters. So that will be the length that she measures. So already our answers are confined so far to either A or B.
Well,
If you know it's got to be different from the original time, then it's already decided.
well, as soon as I looked at it, I was like, all those timings are either equal or bigger. You know?
Oh, that's even better logic. Especially if you're taking a multiple choice test like this.
Yeah.
Mhm.
Trying to
If you
do
took a standardized multiple choice test and you only have a certain amount of time, that's great logic to just think like that.
because the faster you travel, the slower.
It should be a contracted time as well. So in her frame, moving at a velocity equal to 0.8 c, she's got the proper time, and there's a couple ways that you can look at it. She's going to travel this distance at that speed, 0.8 c. So you could say that in her time, it's going to be L divided by her velocity, and that will be 9 times 10 to the 10 meters divided by 0.8 c. And that would give us a time of 375 seconds. Or you could realize that the moving clock runs slow, and so the observer who's in the rest frame should have the dilated time. So her time, in other words, the rest frame time will equal gamma times her time. And so her time will equal the rest frame time divided by gamma. And that was 625 divided by 5/3. 375. So either way you look at it, those are the answers you get. Less time, track the length. All right, so that's all those. Let's save number 3 for last.
Really? I was going to say, when I was working on number 3, I was looking back to problem 22, and if you notice, if you look at 22, the energy differences is just so grand that you pretty much travel very close.
22?
Right. How we had that proton, and then number 3,
Oh, yeah.
we were also using a proton.
Number 3, and you're talking about a lot of energy for this number 3.
Yeah.
So you know you're traveling really,
Really fast.
really close to the speed of light.
Yeah.
Yeah.
Like I had to carry it out to launch this.
Yeah, my calculator wouldn't be able to handle it, but as you know, you can always use an approximation, right? A binomial expansion is probably what it is. Problem number 7. 2 rockets of equal rest length are passing head-on at relativistic speeds, as shown in the figure. Observer O has a gun, and the tail of the rocket pointing perpendicular to the direction of the relative motion. She fires the gun when points A and A' prime coincide. In her frame, the other rocket ship is Lorentz contracted. Therefore, O expects her bullet to miss the other rocket. But in the frame of the other observer, O prime, it is the rocket ship of O that is measured to be Lorentz contracted. Therefore, when the points A and A prime coincide, observer O prime should observe a hit. Does the bullet actually hit or miss? Pinpoint the looseness in the language used to state the problem and the error in one of the figures. Show that your argument is consistent with the results of the train paradox. And yes, I would have chosen this one just because of all that stuff at the end there. So I know you've thought about it. And so what do you think about this one?
I would step out. Like, try to take a step out. Just leave it that way.
Okay, I thought just get out of the rocket
Oh,
ship, let
no,
them
no, no.
fly, let them shoot it out. Step out and think about it from a separate observer.
Right.
We really don't have that luxury.
And
So we have to think of it probably from both observer standpoints. And I think that's the idea. So the leftmost picture is just setting up the problem with the two spacecraft passing each other. The middle picture is the frame of reference of O. So in the middle picture, you've got the Lorentz contracted spacecraft here, and you've got the spacecraft of O. Here's O prime. And the gun is shot when these 2 points coincide. So what you're saying then in O's frame of reference, the coincidence of the 2 points and the shooting of the gun are simultaneous. Right? And so this is a perfectly valid way to see what's going on. In O's frame of reference, these two events are indeed simultaneous. O prime is Lorentz contracted, and the bullet's going to miss. So that is valid for O. Okay. Now there's that third diagram that is supposed to designate how things look to O prime. According to O prime, it's the other spacecraft that's Lorentz contracted. That is perfectly true. Right? Just like the runner with the barn paradox that we talked about Monday. The problem is, what is the problem here?
In this case, it looks like the
where
gun
that
will
bullet
hit.
being hit at the middle of the ship.
It's not going to hit anybody of any importance. Don't worry about it.
Okay.
No, it's
It's starting to hit.
what in the context of other examples that we talked about, what do you think is the answer to this perspective from O prime?
Well, from O prime, it looks like it's going to be hit.
It does if O prime can describe these two events as being simultaneous,
But they don't.
But they're
but
not.
they're not. All right? In the frame of reference of O prime, which is moving this way, the shooting of the bullet occurs first. The shooting of the bullet occurs and passes their spacecraft before they even get there. And then the simultaneity of these 2 points occurs afterwards. So they're coming along like this. This event happens first. They pass that point, and then the event where the two ends meet happens afterwards. So the two events are not simultaneous. like that train example. They did say the train, and it was the train example that we talked about when we were talking about simultaneity, and we had the lightning strikes on both ends of the train. And to one observer, they were simultaneous, and to the other observer, one hit first and then the other one, just like that.
But as the light took
Yes, light took longer. So this cannot possibly be simultaneous to O prime. And so in either case, the bullet does not hit the other spacecraft. Yes.
So, since nobody's made a rocket to go to light speed yet, I know it's not, it's next year, but if they haven't made a rocket that goes light speed, or if they made a rocket with more light speed, then one would assume they would also have a laser weapon by the time.
Okay.
Instead of firing a bullet out of the side of
Well, it could be a tornado.
So,
They fire a
if
laser.
they fire a laser with it, yeah.
No.
Because it's.
I mean, the laser would be even better than a bullet,
Okay.
to be honest.
But I would leave my laser beam on, so I just slice it.
Then you bound it somehow.
Got a question.
But with the light curve, I mean, the laser would curve, so would their mass causing a laser to curve on? Because they were traveling at the speed of light, they would have.
That was,
great kinetic energy
that was
and
part
mass.
D. Consider general relativity on this problem.
Okay.
The curvature of the laser.
In any of these problems of similar nature, from both viewpoints, we have to come to the same conclusion, don't we?
That's right.
Okay.
Yeah. All right, let's look at number 3. Our galaxy is about 10 to the 5 light years across. The most energetic particles known have an energy of about 10 to the 19 electron volts, or about 1.6 joules. How long would it take a proton, mass 1.67 times 10 minus 27 kilograms, for this energy to traverse the galaxy as measured in the rest frame of the galaxy and in the rest frame of the particle? We're looking at this energy of this proton. Relativistically, we'd say the energy is equal to gamma times the rest energy, mc squared. So we can calculate gamma. We can say that gamma should be equal to the energy divided by the mass divided by c squared. And so in this case, that would be 1.6 joules divided by the mass of a proton, 1.67 times 10 minus 27, divided by the speed of light squared. And we get a gamma for this of 1.06 times 10 to the 10. Wow. All right, so in the amount of time it would take to traverse in the frame of the galaxy would be equal to the total distance divided by the velocity of this particle. That's going to be total distance of 10 to the 5 light years. The velocity of this particle is going to be given by c times 1 minus 1 over gamma squared, just using that velocity formula again. So this is 10 to the 5 light years. And the speed of light is 1 light year per year. That's one way that you can describe the speed of light. So that would get rid of light years here. And then we have 1 minus, now gamma is something times 10 to the 10, so we're going to have that effect, where I'm going to use the binomial expansion again, because we're going to have 1 minus something that's extremely small. And so we got, let's say that this is 1 minus 1 over gamma squared to the negative 1/2 power, like that. just brought this up there, like that. So this is 10 to the 5 times 1 minus negative 1/2 times 1 over gamma squared. So this is going to be 10 to the 5 times 1 plus 1/2 or 1 over gamma squared. This term is going to be so small that essentially in the galaxy frame of reference, it's going to be 10 to the 5. The particle's moving so close to the speed of light, it's basically moving at the speed of light. It's going to take 10 to the 5 years for it to traverse 10 to the 5 light years.
Yeah, I was having trouble showing the work on that one because it was traveling so fast.
Yeah. What's it like in the particle's frame of reference? Well, particles, the moving clock runs slow. So the time for the particle is going to equal the time for the rest frame divided by gamma. For the time dilation. And so that's going to be equal to 10 to the 5 years divided by 1.06 times 10 to the 10. And so that will be 9.43 times 10 to the minus 6 years. If we multiply that by 3.156 times 10 to the 7 seconds per year.
296 or so.
Yeah, I'm not sure if this is entirely accurate. About 298 seconds is what I got. Which translates to 4.97. For this proton, it will traverse the universe, or not the universe, the galaxy, in a little bit less than 5 minutes.
Not bad.
Not bad at all. If it could go faster, it could reduce that time. So but you'd have to give it more and more energy. At some point, you'd have to give it infinite energy.
I mean, gamma's pretty much something at all.
Yeah, that's pretty large.
Is that it?
That's it. What do you think?